So this continues the tutorial on church encoding. And now I will talk about church encoding of more complicated types. The previous tutorials talked about simple recursive types for simplicity only. Certainly not very useful to have just a simple type defined recursively like natural numbers. So I'm going to talk about first mutually recursive types to get it over with. So suppose you have a type that you would define in Haskell just with no particular ceremony. Let's say layer depends on itself and on some layer 2, and layer 2 depends on layer. So this is a kind of a tree with complicated branching. In Dhall, we cannot write a definition like this because it's recursive. So how do we rewrite it? The first step is to introduce pattern functors. So in other words, we want to write it in this way so that layer is a pattern functor that is applied to layer and layer 2. Layer 2 is another pattern functor applied to layer and layer 2. So that's kind of a general formulation for mutual recursion. Now clearly these f1 and f2, they must be functors with two type parameters, or bifunctors as they're called. And clearly this is how we would define this in Haskell in order for this to be equivalent to that definition. So just like in our previous definition of the church encoding, that's the first step where we introduce non-recursive pattern functors, and that is clearly easy to implement in Dhall because that's not recursive, so we just rewrite it in Dhall like this. And then this is the main thing here that's not very easy to understand maybe. You use the church encoding with these two pattern functors in the following way. So it's similar to the usual church encoding where you have for all A and then fa to A. Here you need to have two type quantifiers for all A and for all B, and then you need two functions as arguments of this higher order function, and one is f1ab to A, f2ab to B. Finally, the result must be A here, and here it's exactly the same argument types except for the result, and the result is B instead of A. And that is a very important difference. Now certainly it is by no means obvious why this set of types is actually equivalent to the mutually recursive types that you would define in Haskell in this way. It's by no means that is obvious and clear. You can kind of see the intuition that if you have a function of this kind, a function of that kind, that you should be able to recover this. This intuition is certainly not enough to justify this formula. Why do we need both of these arguments? Why not just one of them? Just f1 for the first one and f2 for the second one, for example? Not clear. So the only way to see that this is correct is really to prove that this is correct. Now the proof, I'm showing that proof in the appendix of this tutorial, of the text. I'm not going to go through the proof right now. So, but I'm just going to show you this for a reference, and this is a general way that is easy to generalize for more mutually recursive types. You could clearly see the pattern. If you have 5 recursive types, and you would have 5 pattern functors, each with 5 arguments, and then you would have here 5 arguments in this higher order function, f1 a, b, c, d, e to A, f2 a, b, c, d, e to B, F3 ABCDE to C, and so on, until F5 ABCDE to E, and then this will be to A, this will be to B, to C, to D, to E. And similarly, you would have to prove that this is correct, but this is beyond the scope of my current tutorial. And most of the time in this tutorial I'm going to spend on type constructors. So recursive type constructors such as lists and trees are the bread and butter of ordinary functional programming, and that's what we're going to talk about today. So how to encode such recursive type constructors that have the form of the definition not like this, but with type parameters. So TA is something like that. So there's some pattern functor which depends on A as well as on TA. So in order to describe this with a church encoding, we need again a pattern functor that has more type parameters. As an example, let's take the binary tree, which you would define in Haskell like this. The pattern functor needs to be a bifunctor with two type parameters. So the first type parameter is this data type A, which is not involved in the recursion directly. It is just the data that is going to be stored in this tree. And then R is the type parameter that describes recursion in this type. So the branch type has two copies of R here, which correspond to this. Now, very important is that this definition defines tree A again through tree A, and not through some tree B with some other type B. So it's very important. It's a very simple kind of definition. We can just temporarily pretend that A is a fixed type, not a type parameter, denote tree A by R. This will be just a fixed type, and this will be branch RR. So that shows how this definition is really equivalent to defining a simple recursive type that doesn't have type parameters, holding A as a fixed type, and then you can just use the church encoding, which is for all R, FARR to R, like this, FAR to R to R. Except, so this is exactly similar to the church encoding that we have seen before, except there's an extra type parameter A here, and there's a type parameter A in front of this entire thing, which means that in this type expression, the type parameter A is fixed. It is given and bound before, outside of this. So that is exactly what I was talking about, and this is why the church encoding for tree can be written in this way. Now, if here, this would be not a tree, but some other more complicated type, let's say here you had not A, but a pair of AA, then this encoding would not work. And I will not talk about such more complicated cases now, because they're rarely used. Trees are encoded like this. Now, the beauty of system F omega is that you can parameterize this by F. So you can write a general definition of a church encoding for a type constructor given any pattern functor F. So you can make a pattern functor F into a parameter, and this is how you would do that. So we define this constructor, type constructor, which is a function of an arbitrary bifunctor F, and then it takes an argument of type parameter A, and then it gives you the church encoding of the fixed point defined by the type, the pattern functor f having the type parameter a, still free. So then with this combinator, we can just define tree like this very quickly. And then, similarly to what we did in the with the church encoding in previous tutorials, we can compute general properties of this type. We can have fix and unfix. We can have, it's very easy because fix and unfix were parameterized by the pattern functor, as long as we have a functor type class evidence. And now we have in this kind of pattern functor, but one of its type parameters is going to be a fixed type A, so we can just substitute in there and have a functor instance for that functor where A is already substituted, and that's enough to just use a standard fix function to get what we need. So in this way we can quickly define fix and unfix for type constructor fix points. So I denote them fix t and unfix t. Now, if you look at this, it's a lot of lambdas here, that's true, but each of them plays an important role. So we have a parameter f, parameter a, and then there's a type class evidence for functor of fa, and that's sufficient. We don't really care that f is covariant in A. We don't need that at this point. Just to define fix, we don't need that. So it could be that f is contravariant in A. We still have a well-defined fix point and a well-defined type constructor. So it is not actually limited to covariant type constructors. This way we can define also contravariant recursive type constructors. The pattern functor f must be covariant in its second type parameter, right? So pattern by functor f has two type parameters. The second one is the one that describes recursion, and it's in that second type parameter that the pattern functor f must be covariant, but not necessarily in the first one. And so we only need the functor evidence for this functor, which is f with the first type parameter already substituted and still waiting for the second type parameter. And for that functor, we need a type class evidence. And then, given that, we just apply fix with the correct type parameters and we're done, or apply unfix. And certainly we can do the same with more type parameters. We can have a data type with any number of type parameters. All we need to do is to put these type parameters into the f and have enough lambdas in front and we're done. Now, if you compare this with the Haskell syntax, this is not written in the Haskell syntax. Lambda A type, lambda B type, that is just implicit in this syntax. So if you write a data type definition with type parameters, it is implicit that they are type parameters. You don't have to put lambdas in front of them or annotate their types. By assumption, these are just ordinary types. But in Dhall, you have to annotate. And actually it shows you what is going on more clearly. So this could be, you see, some type parameters have a different kind. In Haskell, you would sometimes have to indicate that too, but in many cases you don't. And that makes it harder to remember and to understand the code without help or comments. In Dhall, everything is explicit, and so yes, you have to type more, but probably with some tooling, we wouldn't have to type all of this. But in any case, it shows you everything that plays a specific role. And this is, for example, lambda, and this is the universal quantifier, and not the other way around. So in this way, Dhall has a verbose syntax that actually helps me understand what's going on and not make mistakes. And really understand how these constructions work. So let's see, as an example, we can encode lists. The ordinary list constructor is encoded like this in Haskell, but this is recursive. But see, the recursion has a simple form where list A is expressed again through list A and not through list of some other combination of types. And so we can again do this trick where we pretend temporarily that A is a fixed type, so we put a lambda A in front, and in here A is a fixed type in this scope, and so then we just put A as a first argument of this pattern functor, and we just use lfix on it. Or we have a combinator that does this in a shorter syntax. Well, certainly we need to define functor evidence for this. Then we get a fix. We derive data constructor functions, which will have a type parameter now. We do the same things that we did with ordinary church encoding, but everything will have a type parameter. So data constructors will have a type parameter. Nil has a type parameter. Const has a type parameter. So you cannot just have nil. You must have nil with a type. Similarly to Dhall, you cannot write in Dhall. You cannot write just an empty list. You have to say of which type that is, and this is exactly why. So you have this type argument, so you have to write, for example, here nil CList natural. So const CList natural 5. So everywhere you have to write natural, 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 natural. So certainly for brevity you could define this partially applied function as some other name, and that it will have less to write. A lot of things can be implemented directly via the church encoding. In other words, non-recursively with short code, concatenating lists, for example, and reversing lists, and so on. Now, because list already is a built-in type in Dhall, let's consider non-empty list, which is not built-in, slightly different from ordinary list, also has interesting properties. This is the recursive definition that you would write in Haskell. The bifunctor f for the pattern functor here is like this, and so you just do the church encoding, and then the data constructors, and here's how you construct values of this type. You have data constructors more and last, so that's how I call them. Or you can do the curried church encoding, which would look like this, and then you're on your own defining all the functions by intuition and testing. Because you see, these data constructors, which are in non-curried form of the church encoding, where this is just a single function from a union type, in that form you can derive everything generically. You can derive all the data constructors, fix and unfix and so on, generically, and just apply. You can, as long as you have the bifunctor instance for this, you can just apply generic combinators. But if you are working with the curried church encoding, you're kind of on your own writing the code by hand. So the data constructors need to be written by hand, because you cannot derive fix and unfix here. There is no functor f that is explicit, and this is a bit of a difficulty. You could just define converters from the curried to uncurried and back, and then you could get everything automatically. But it's also instructive to see how that works by writing it by hand. So for example, how does 1 work? You take a type r, you take this, and you just use this function ar on the x that you're given. That's the single element non-empty list. And the cons operation need to do more work. And for testing, you convert them to list. You write a function that converts to list, and that is just clear. So the function converting to list is an application of this to a list A type, and then you have to provide functions of types A to list A and A to list A to list A. So that's what you write here. And then you write tests. So element 1 to 3, and you reverse 3 to 1. So all these different examples. We're going to implement concatenation and reversal. So concatenation is implemented like this, and the lfold is just an identity function, really. It applies this to the two functions here. And so let's assert that you have concatenation, and that really works. Reversing a list, we append at the end, which requires us to have a different function for appending at the end, which is concatenating with a one element non-empty list. And then we do reversal. It's not very performant. As I already discussed in the previous tutorial, performance of church encodings is not very great. It's so concatenation is linear and reversal is quadratic. I showed, however, now since the last tutorial I have completed this text and the book. So I actually have timings, and I see that, for instance, computing the sum of the list is 0.5 seconds, and actually head optional and concat was very quick. So not all operations are so slow, but certainly some are. Let me comment a little bit about the head optional, because that's a little piece of intuition that is maybe interesting. If you do the head optional, then actually what you need is you take this function, which is this hard-coded application of the function a2 3 times, let's say, in this example, and you need to find out if this function has been applied even once or not. So actually head optional will give you sum plus 123 on this example. How can it be that this is linear, this is constant time and not linear in the size of the list? Because it looks like I'm applying a2 3 times. The reason is a2 can be lazy in one of its arguments and actually can ignore one of its arguments. In that case, Dhall has lazy evaluation, and let's say a2 is a function that takes an integer, ignores this argument, and returns, say, that integer, or sum of that integer. Then this computation will ignore all of that, and it will not be computed because Dhall uses lazy evaluation. And so that's why, even though it looks like we're going to evaluate a lot of things, we're actually evaluating a constant time operation. So this happens when we apply the church encoded data to functions that are that ignore some of their arguments, and that's very, very fast, so in some cases. So that's actually a good thing. So for example, checking if a list is empty or not, or taking a head option is constant time, even though in strict evaluation this would be linear time. So concatenating is actually linear time, but in some cases it it can be constant time, even though we're using church encoding. So let me go back to an interesting example of zipping. Now, zipping is an operation that's not obvious. I implemented here zipping in two different ways for non-empty lists. And the first way is to apply repeatedly tail optional. So I'm having a fold over the first list, and I keep the tails of the two lists in the accumulator. So the accumulator has a result and the two tails. And then I use a natural fold with the length, which is a minimum of the two lengths of the two lists. So I'm repeating the operation where we take the head of the first list, the head of the second list, and see if one of and put the two values into a pair and append. It's a very slow code because every time we need to do head optional and we need to do tail, and the tail is a linear operation on church encoded lists. And head optional is so the head operation is constant time, but the tail operation is linear in the list size. So this is going to be zip is going to be a quadratic operation essentially. And there are other ways of implementing zip, but there's no escape from this slowness. And here I tried to implement zip directly in the church encoding by just trying to see, okay, I have some functions here. I have a lot of functions. Can I just combine them somehow? So I have null A, null B, so these are higher order functions. Can I combine all of this somehow to get the result of the correct type? And I'd like to avoid ignoring values, because if I ignore them, I can just ignore a lot of values and it won't be a very useful function. So yes, I can write some kind of code guessing what to do, but the result is that the zip operation gives me not so the zip between 1 to 3 and 4, 5. It gives me a list of 6 elements enumerating all combinations of elements from one and elements from the other. And that's not what I was waiting for. That's kind of a zip operation that programmers don't expect to have. However, it is a lawful zip operation. It is a zip operation that you can get if you define an applicative instance through monad, if you know what I'm talking about. So it is satisfying the laws of zip, but it's not what you want. So I talk about zip in another chapter in this book. It's a complicated topic because zip is a difficult operation, it turns out. And generally, applicative functors are not easy to work with in System F. Finally, let me show you what else you can do. So actually, given any church encoded data constructor, you can compute the size and the depth of recursion in that data. And you can compute that generically, it turns out. So you need to traverse a data structure, accumulate some naturals, and I show here how to do that. So all you need to do is you need to supply a function from type of type f a natural to natural. And if you supply this function, then you can use a fold, or you can just apply the higher order function, that's the church encoded data, to this function. And having this function in the correct way will give you the size or the depth. So for example, how do you do the size? Now, you know what f is, right? So let's say f could be no data of type A or one element of data of type A or something like this. So depending on this, you know how many A's are in here. And this argument gives you how many A's are in the recursive parts. So there can be several of those. So you sum all of that, you summed all of this together, and that's the result. So that gives you the size, which is how many items of data of type A are inside this entire structure. And similarly, depth. So you take the depth from here and you add 1 if you are here. So that's a very simple calculation. This is an example of how to do this with lists. So you supply this function from this to natural. And if you are in this variant, then you have 1 item. And if you are here, you have 1 item here and then some items there. And you add this together, you get the size. For binary trees, you need to add the left subtree and the right subtree here. So that is how you do that. So the depth calculation is similar, and we can, interestingly, you can define a generic way of computing size and depth as long as the pattern functor f is foldable. And if it is foldable, it means that it needs to be foldable with respect to both type parameters separately. And if that is so, then you can enumerate all of the data items of type A inside FAB and all of the data items of type B inside FAB. And that's what you need to compute these functions for size and depth. And then I show how to do that generically. So I have size f, depth f, which are parameterized by an arbitrary pattern functor f, as long as it is foldable in both in both parameters. So this is the result, and you can just use that to compute the size and the depth of some examples. Finally, if you have a functor evidence with respect to the first type parameter, then you can implement the functor evidence for the fixed point type. So that is relatively easy to do. So let me conclude this part of the tutorial here. So this is how you work with type parameters that are defined recursively. In the next part of the tutorial, I'll talk about yet more complicated types, like existential types and church encodings for higher kinds. And let me conclude by saying that at this time, the entire book is ready. You can get it on LeanPub, and if you want on paper, you can get it from lulu.com for a very high price, but this is what you have to pay nowadays for paper books, printed on demand. You don't have to do this. It's a free book, so free in terms of freedom, and the entire source code is in this repository. This concludes this part of the tutorial.